In the spring of 66 million years ago, a season we know now because scientists read it in the bones of fish that died on that very day, the sky above what is now Mexico's Yucatan Peninsula fractured. A carbonaceous chondrite, 9 to 15 kilometers wide, traveling at roughly 20 kilometers per second, struck a shallow sea at an angle of perhaps 60 degrees. The impact released energy equivalent to 10 billion nuclear weapons detonated simultaneously. And in that single afternoon, the longest experiment in vertebrate history, 165 million years of dinosaur dominance, was interrupted. The question the record cannot answer is a simple one. What if it hadn't been? The location is Hell Creek Formation, North Dakota. The land here is quiet now, short grass, low hills, the slow erosion of badlands that no one visits without a reason. There is a riverbed beneath the soil that has not held water for 66 million years. In 2012, a paleontologist named Robert De Palma began excavating a section of it that commercial collectors had flagged as unusual. What he pulled from the ground would be argued over for the next decade. A leg, intact, belonging to a dinosaur that had been alive that morning. Fish with glass beads embedded in their gills. Fragments of plant material still carrying their cellular structure. A sliver of rock, no larger than a coin, whose chemistry matched no deposit within 1,000 kilometers. The records of that day were buried in 13 minutes. They are still being recovered. What follows is the record of the day the world changed, and the 13-minute window in which the change was decided. The file on the end of the Cretaceous is older than most of us realize. It is also, in places, still being written. There is the asteroid that arrived from the outer reaches of the solar system. There is the wrong rock it struck, sulfate-bearing, deposited over millions of years by the slow evaporation of ancient seas at the wrong angle, in the wrong season, on the wrong day of the Earth's rotation. There is a 1,982 paper, peer-reviewed and largely forgotten outside specialist circles, that mathematically described what the dinosaurs would have become if any one of these conditions had been different. There is a leg in a North Dakota basin that should not exist, belonging to a creature that was alive at sunrise and buried by noon. The records keep returning to this morning. This is its file. To understand what was lost requires first understanding what was there. The late Cretaceous is not, in the records, a single world. It is a sequence of worlds, each one occupying the same planet but bearing little resemblance to the one we now stand on. 66 million years ago, the continents were not yet in their modern arrangement. North America was split down the middle by an inland sea, the Western Interior Seaway, that stretched from the Arctic Ocean to the Gulf of Mexico, a distance of nearly 4,000 kilometers. The continent was effectively two large landmasses, Laramidia in the west and Appalachia in the east, separated by warm, shallow water averaging perhaps 100 meters in depth. The Rocky Mountains existed but were younger and lower than they are now, still rising. The Great Plains were submerged. What is now Denver sat beneath several hundred meters of ocean. The city that would one day excavate and display these fossils was itself, at this moment, a seafloor. Australia was still attached to Antarctica. Antarctica was not ice-covered. It was forested conifer forests in some regions, broadleaf forests near the coasts, and it had been drifting southward for millions of years without yet reaching the position of isolation that would produce its modern ice sheets. Fossils from late Cretaceous Antarctica include ankylosaurs and hypsilophodontids, small plant-eating dinosaurs that had adapted to months of polar darkness and temperate cold, not to ice and glaciation. The continent was cold compared to the tropics, but it was alive. India was an island. It had broken from the supercontinent of Gondwana approximately 130 million years earlier and was drifting northward across what is now the Indian Ocean at a rate of roughly 15 to 20 centimeters per year. Faster than most tectonic plates move. The Himalayas do not yet exist. The Tethys Sea, a warm, shallow ocean that no longer exists in any recognizable form, occupied the space between the Indian subcontinent and the rest of Asia. When India finally collided with that landmass, tens of millions of years later, the Tethys Sea would be closed, and the seafloor sediments that had accumulated in it would be folded upward to form the highest mountains on Earth. None of this had yet happened. The Atlantic was narrower than it is now. Europe and North America were separated but intermittently connected by land bridges that allowed faunal exchange. The Pacific was larger. The configuration of ocean currents, shaped by this different arrangement of continents, produced climate patterns unlike anything in the historical or instrumental record. The climate was warmer than ours by an average of 4 to 6 degrees Celsius. Some estimates, based on oxygen isotope ratios in fossil shells, put it higher, as much as 8 degrees above current averages in some regions. There were no permanent polar ice caps. Sea levels were higher, flooding continental interiors. The poles supported temperate forests. Crocodilians, large, semi-aquatic predators we now associate with the tropics, lived above the Arctic Circle. The ocean surface temperatures in what is now the North Atlantic were comparable to those of the modern Caribbean. In this warmer, wetter, more equitable world, dinosaurs occupied every continent and every major ecological role available to large land animals. By the most recent census of the fossil record, more than 1,000 species are formally described and named. The actual number of species that existed across the full extent of the Mesozoic is estimated at several times this figure. Most lineages left no fossil trace at all. The record captures only those animals that happened to die in the right conditions, in the right locations, to be preserved by the sediment that later became rock. It is a sample, a small one. What is sometimes forgotten in the popular telling is the scale of what the dinosaurs represented: not merely a group of animals that happened to be large and dramatic, but a dominant terrestrial lineage, continuously evolving and diversifying for 165 million years. The entirety of human civilization, the first cities of Mesopotamia, every empire, every written language, the printing press, the Industrial Revolution, the space program. The present moment occupies roughly the last 6,000 years. The Mesozoic was older than that by a factor of nearly 30,000. The dinosaurs did not merely exist for a long time. They ruled. They held the dominant ecological position on land for a span of time that makes human history look like a single afternoon. Their reign was not a plateau, it was a continuous process of change, extinction, and emergence, producing new lineages in each geological period, filling new niches as the planet itself changed around them. By the late Cretaceous, the most recent phase of this long experiment had produced a particularly complex and stable biosphere. The record shows a world that had reached, in ecological terms, a kind of equilibrium. It was not static, it was not unchanging, but it was, by all available evidence, a functioning world, complete, ongoing, about to be interrupted. By the late Cretaceous, the major dinosaur lineages had stratified into ecological roles that look, from the geological distance of 66 million years, almost familiar: apex predators, grazing herds, armored defense specialists, ambush hunters, filter feeders. The vocabulary is not foreign, only the animals filling those roles are. Tyrannosaurus rex occupied the apex predator niche in western North America, Laramidia. The fossil record preserves it in reasonable detail. A binocular-visioned predator with a bite force estimated at around 35,000 newtons, the highest of any land animal yet studied, capable of crushing bone and extracting marrow. Recent research suggests it may have been partially covered in scales rather than feathers, and that it grew rapidly in adolescence before slowing in adulthood, producing the variation in size that appears in different specimens. Whether it primarily hunted live prey or scavenged is still debated. The record is insufficient to settle it. What is clear is that it stood at the top of a food web that sustained some of the largest herbivores in the history of terrestrial life. Triceratops grazed the floodplains of the Hell Creek Formation. It was not a single static species. The record shows morphological variation across different strata, suggesting evolutionary change even within the final 2 million years of the Cretaceous. Edmontosaurus, a hadrosaur, traveled in groups. One trackway site in Alberta preserves the movements of what has been estimated as a herd exceeding 200 individuals, with juvenile track patterns suggesting the young move toward the center of the group, flanked by larger adults. This is behavioral evidence. Behavior rarely survives in the fossil record. The fact that it does here, encoded in the geometry of footprints in what was once riverbank mud, is a reminder of how much information the record contains when the conditions for preservation are right. Ankylosaurs, broad-bodied, short-legged, armored across their upper surfaces with fused plates of bone and skin, and bearing a massive bony club at the end of the tail, move through the underbrush in a manner functionally similar to modern armadillos, heavily defended and slow to alarm. Pachycephalosaurus, with a skull reinforced by up to 25 centimeters of solid bone, occupied an ecological role for which there is no precise modern analog. Whether it used its dome in head-butting displays, in combat, or as some form of thermoregulatory surface remains unresolved, the record preserves the dome. It does not preserve the behavior. In the air, pterosaurs had reached their maximum size. Quetzalcoatlus northropi, from the western interior of North America, remains the largest flying animal in the known fossil record. Its wingspan has been estimated at 10 to 12 meters. Standing on the ground, it was as tall as a modern giraffe. It is thought to have launched itself into flight, using all 4 limbs pushing off with its wings as well as its legs, and to have traveled thousands of kilometers on thermal currents in a manner analogous to the wandering albatross, touching down infrequently. It shared the late Cretaceous sky with smaller pterosaur species, and with the early birds, true birds, descended from theropod dinosaurs, already diversified by this period into dozens of lineages, some coastal, some forest-dwelling, some toothed, some not. In the seas, mosasaurs had become the dominant marine predators. They were not dinosaurs, they were monitor lizard relatives that had returned to the sea and expanded over tens of millions of years to fill roles analogous to modern orcas and great white sharks. Mosasaurus hoffmanii reached lengths of 17 meters. They shared those oceans with plesiosaurs, long-necked, flippered marine reptiles whose lineage had begun in the Triassic and persisted, largely unchanged in body plan, for over 100 million years. Both groups were at their maximum diversity in the decades before the end. And then there were the mammals, small, burrowing, mostly nocturnal. The largest known late Cretaceous mammal, Repenomamus robustus, was the size of a medium dog, approximately 14 kilograms. This was exceptional. Most were much smaller. They had occupied the margins of the dinosaur world, the underbrush, the burrow systems, the night for over 150 million years. They were not waiting for an opportunity. They were occupying the niches available to them. Those niches were small because larger niches were taken. The Hell Creek Formation captures the final 2 million years of this world in unusual detail. The fossils show a stable, complex ecosystem. There is no obvious sign, in the bones themselves, of a world about to end. The dinosaurs are well represented at all body sizes and in all ecological roles. The record shows them going about their lives, migrating, grazing, hunting, nesting, in a world that had operated by these rules for an immeasurably long time. This is, perhaps, what makes the record difficult to hold in mind for long. The object that ended the Cretaceous was not, in cosmic terms, large. It was approximately 10 to 15 kilometers in diameter, roughly the height of Mount Everest, laid sideways. At the scale of the solar system, it was a speck. At the scale of Earth's biosphere, it was an extinction. The most recent chemical analysis, published in 2024, identified it as a carbonaceous chondrite, one of the most primitive classes of solid material in the solar system. Carbonaceous chondrites are thought to preserve material from the earliest phase of solar system formation, approximately 4.56 billion years ago. They contain not just rock and metal, but water, bound into hydrated minerals and organic compounds, amino acids, aromatic hydrocarbons, the molecular precursors of biochemistry. They are, in a sense, relics of the molecular cloud that collapsed to form the sun and the planets. Many of them predate the Earth itself. The origin of this particular object is still debated in the literature. The conventional hypothesis places the source in the outer asteroid belt, between the orbits of Mars and Jupiter, where the gravitational influence of Jupiter can perturb object orbits enough to send them onto Earth-crossing trajectories. This is the standard mechanism, and it is well supported by orbital mechanics. Many known near-Earth asteroids follow paths traceable to this region, but a 2021 paper by Siraj and Loeb proposed a more unusual origin. Their analysis of the impactor's probable composition, combined with dynamical models of how the sun's tidal field perturbs objects during close approaches to the galactic center, suggested that the object may have originated in the Oort cloud, the vast, sparse, spherical reservoir of comets and icy bodies that surrounds the solar system at distances of up to 1 to 2 light-years from the sun. In their model, a long-period comet, on an orbit that brought it close to Jupiter, was broken apart by tidal disruption, and one fragment of this disrupted object followed a modified orbit that eventually intersected with Earth. If this is correct, the implications are considerable. From the Oort cloud to the inner solar system is a journey of tens of millions of years at cometary velocities. The object would have spent most of its existence in a region of the solar system where the sun is not the dominant gravitational influence, where passing stars, molecular clouds, and the broad gravitational field of the Milky Way matter more than planetary perturbations. It would have passed through complete darkness, at temperatures near absolute zero, for a span of time longer than the entire Cenozoic era. It would have entered the inner solar system as a traveler from a place without a name, shaped by forces that operated on timescales the fossil record cannot resolve. The probability that any given Oort cloud object will ultimately strike Earth is vanishingly small. The Oort cloud contains an estimated tens of billions of objects, possibly more than 1 trillion. Most of them will never approach the inner solar system within any time frame relevant to the history of life on Earth. A fraction will be perturbed inward by the gravitational influence of nearby stars, or by the tidal field of the galactic plane, over millions of years. A fraction of those will cross Earth's orbit. A fraction of those will arrive at the same moment in Earth's orbit as Earth itself. The records of those interactions, the gravitational negotiations that sent this particular object on this particular path, are no longer recoverable. They occurred over geological timescales, in regions of space that no instrument we currently possess can survey in detail. What is preserved is only the moment of arrival. It struck at approximately 20 kilometers per second. In the final seconds of approach, it would have been visible as a brilliant point of light moving across the daytime sky faster than any object a Cretaceous eye had ever tracked. The atmospheric column in its path compressed and heated. The sky above the Yucatan brightened. The shallow sea below it began to absorb the leading edge of a pressure wave traveling at the speed of sound. The sea evaporated. The site of impact was a shallow carbonate platform off the northern Yucatan Peninsula. A warm tropical sea, no more than 100 meters deep in most places, underlaid by one of the thickest deposits of sulfate-bearing rock on Earth. The crater the impact left Chicxulub, named for a small village near its center, is 180 kilometers in diameter. It is buried beneath a kilometer of younger sediment and was not detected until 1978, when geophysicists Glenn Penfield and Antonio Camargo conducting an airborne magnetic survey for the Mexican national oil company Pemex, found an arc of anomalies in the Gulf of Mexico that could only be explained by a buried circular structure of unusual scale. Their finding was not recognized for what it was for another decade. The paper they eventually published in 1981 attracted almost no attention at the time. The record of the crater's discovery is, itself, a quiet one. The energy released by the impact has been estimated at approximately 10 billion times the yield of the largest nuclear weapon ever detonated by humans, or about 100 million Hiroshima bombs, released in a fraction of a second. At this scale, the figures are difficult to make meaningful. What can be said concretely is that the target rock was not merely shattered or melted. It was vaporized, converted directly from solid to gas by the shock pressure of the impact, which exceeded the compressive strength of rock by many orders of magnitude. The impactor itself largely ceased to exist as a discrete object. Its material mixed with the vaporized rock to form a rapidly expanding plasma, which punched through the atmosphere and dispersed into the stratosphere and beyond. The crater excavated in the first seconds was more than 30 kilometers deep before the crust rebounded. This rebound, driven by the elastic properties of rock under extreme pressure, created a central uplift, then a ring of ridges, then a broader ring of collapse. The concentric structure that deep drilling and seismic surveys have since mapped in detail. The structural geology of the Chicxulub crater is now among the best understood of any large impact structure on Earth, largely because it was still geologically young when it was found, buried but not deformed. Above the crater, a column of material rose into the stratosphere within seconds and began to disperse globally. The largest fragments, rocks ejected at near-orbital velocities, traveled outside the atmosphere entirely, arcing around the globe before re-entering hours later. As they descended through the upper atmosphere in large numbers, frictional heating raised the global atmospheric temperature significantly for a period estimated between 1 and several hours. This heat pulse was intense enough to ignite surface vegetation across wide areas of the northern hemisphere. The charcoal layers preserved in KPG boundary sediments found in Cretaceous rock on every continent are the record of those fires. Tsunamis radiated outward from the impact site at speeds exceeding 800 kilometers per hour. The largest, in the near field, have been estimated at more than 300 meters in height. They struck the coastlines of what would become Florida, Texas, and the Caribbean within 1 to 2 hours. They entered the shallow western interior seaway and traveled northward. Simultaneously, seismic waves generated by the impact were propagating through the Earth's crust at several kilometers per second, arriving in distant regions in minutes. In what is now North Dakota, approximately 2,800 kilometers from the impact site, those seismic waves arrived in roughly 10 minutes. The water in the low-lying river systems responded to the ground motion with Seiche's resonant standing waves that surged up the river valleys, carrying everything with them. The sulfur entered the stratosphere in the first minutes of the event and did not leave. At stratospheric altitudes, above the weather, there is no rain to wash out aerosol particles. The sulfate particles spread globally on stratospheric winds within weeks. Within a year, the entire planet was beneath a veil of sulfate aerosols that scattered and absorbed incoming sunlight, reducing surface temperatures by an estimated 10 to 26 degrees Celsius, the range reflecting different modeling assumptions for a period of at least 2 years, and possibly longer. Photosynthesis slowed. Then it failed, in many regions, entirely. The food web depends on photosynthesis at its base, on the conversion of sunlight into chemical energy by plants and algae. When photosynthesis collapses, the collapse propagates upward through every trophic level. Herbivores starve, carnivores starve. The largest animals, with the highest energy requirements and the lowest reproductive rates, go first. The smallest, the most generalized, the burrowing and the dormant, last longest. The world that had existed for 66 million years was interrupted in the early afternoon of a spring day. The darkness that followed took years. The recovery took millions. The Tanis fossil bed sits in the Hell Creek Formation, near the small town of Bowman, North Dakota. It was first explored systematically in 2012 by Robert De Palma, then a graduate student at the University of Kansas, who had been directed to the site by commercial fossil collectors working the region. They had told him it contained unusual concentrations of fish fossils. He went to confirm. What he found, by his own later account, was something nobody had anticipated finding. The bed itself is approximately 1 1/3 meters thick. Within that 1.25 meters are tens of thousands of fossils, packed together in what appears to be chaotic deposition fish, with their tails pointing in multiple directions. Tree trunks, whole branches, mammals, a leg belonging to a small dinosaur, fragments of pterosaur wing membrane, ammonite shells from the sea. The fossils show no signs of the normal decay and sorting that occurs when remains accumulate over years or decades. They are jumbled, as if deposited in a single rapid event. Above the bed lies a thin clay layer rich in iridium, the geochemical signature of the asteroid impact, found at KPG boundary sites on every continent. What made Tanis different from every other KPG boundary site was what was inside the fish. Lodged in the gill arches of preserved sturgeon and paddlefish were tiny glass spherules, millimeter-scale droplets of molten rock ejected from the impact site, which had cooled into glass spheres during their flight through the upper atmosphere. The fish had inhaled them while gulping water in a disturbed environment. The geochemical composition of the spherules, the ratios of their trace elements, the isotopic signatures of the minerals that crystallized inside them matched the rock composition of the Chicxulub crater. De Palma's team concluded that the Tanis bed had formed not over years, not over days, but in hours. The seismic waves from the impact, traveling at several kilometers per second through the Earth's crust, reached North Dakota in approximately 10 minutes. The water in the river valley responded to the ground motion with Sisha's resonant standing waves, driven by seismic energy rather than distant tsunamis that surged repeatedly up and down the river valley, excavating and redepositing sediment with each surge. The spherules arrived from the upper atmosphere within the first several hours, falling like hot rain into the disturbed water. The fish, stressed and disoriented in the churning river, gulped water and drew the spherules into their gills. They died. The sediment settled. The iridium arrived later, as the global dust cloud dispersed over weeks and months, settling in a thin layer over everything. The discovery has been significant and contentious in equal measure. A 2023 investigation by the University of Manchester found evidence of poor research practices in some of De Palma's published work, while stopping short of a finding of fabrication. The papers describing Tanis have not been retracted, and the core physical evidence, the iridium layer, the spherules, the fossils, the stratigraphic context, has been confirmed by independent researchers who have visited the site. The interpretation of that evidence, specifically the claim that the entire deposit formed in the first 13 minutes to first several hours of the post-impact world, is still being tested and debated. What can be said with confidence is this: the bed exists. The iridium layer caps it. The spherules are real, and their chemistry matches the crater. Whatever the bed records, it records something that has not been found anywhere else in equivalent detail. The leg of the Thessalosaurus, a small bipedal herbivore about the size of a large dog, unremarkable in the late Cretaceous ecosystem, was found articulated, which means the bones were still in their correct anatomical positions when they were buried. This indicates rapid burial, before the ligaments holding the bones together had time to decay. The animal had been alive that morning. By noon, it was beneath the mud of a surging river, alongside fish with the sky's glass in their gills. The records of that morning continued to be recovered, slowly, from the sediment. De Palma returned to the site in subsequent years. The excavation continued. Additional material was recovered, documented, disputed, and analyzed by independent teams. The site became, in the decade after its initial publication, one of the most carefully scrutinized fossil localities in the world, scrutinized not only for what it contained, but for the claims made about it, and for the question of whether those claims were supported by the evidence with the rigor the evidence deserved. This scrutiny is the record working as it is supposed to work. The details are tested. The claims are examined. What survives, examination becomes part of the record. What does not is noted and set aside. What has survived so far is the bed itself, the spherules, the iridium layer, and the leg. The Earth, 66 million years ago, rotated at roughly the same speed it does now. A point on the equator moves through space at approximately 1,500 kilometers per hour as the planet turns. Across 13 minutes, such a point travels approximately 325 kilometers westward relative to any fixed object in space. 325 kilometers. That is the figure that haunts the literature on this event. Not the energy, not the crater dimensions. The 325 kilometers. The asteroid that struck the Yucatan Peninsula was on a trajectory determined by celestial mechanics, by the gravitational interactions of every body it had encountered over millions of years of travel. Its arrival time at Earth's orbital distance was, by the time it was hours from impact, essentially fixed. The location it would strike, however, was determined not by its trajectory but by where Earth happened to be in its rotation at the moment of arrival. A rotating planet presents different faces to the same incoming object depending on the precise time of impact. 13 minutes earlier, and the Yucatan Peninsula would not yet have rotated into the asteroid's path. The strike would have occurred in the Pacific Ocean, west of Mexico, in deep water. 13 minutes later, and the strike would have fallen in the Atlantic, east of the Yucatan, also in deep water. This is not speculation introduced after the fact for dramatic effect. It is the conclusion of a peer-reviewed study. In 2017, Kunio Kaiho and Naga Oshima of Tohoku University published a paper in the journal Scientific Reports that modeled the climatic consequences of impacts at different points across the Earth's surface. Their methodology was straightforward. They identified regions of the Earth's crust that are underlaid by sulfate-rich rock, specifically anhydrite and gypsum, calcium sulfate compounds that form when shallow seas evaporate, and modeled the atmospheric sulfur injection that would result from an impact at each type of target. Their finding was that approximately 13% of the Earth's surface area consists of the sulfate-bearing shallow continental shelf rock necessary to produce a mass extinction. The other 87% does not. An impact in deep ocean basalt would vaporize basalt. Basalt does not contain sulfur in significant quantities. An impact in granitic continental crust would vaporize granite. Granite is poor in sulfur. Only an impact in the specific kind of carbonate anhydrite platform that underlies shallow tropical seas would inject enough sulfur into the stratosphere to produce a global climate effect of sufficient severity to cause a mass extinction. The Yucatan Peninsula, in the late Cretaceous, was precisely this kind of platform. For tens of millions of years, a warm, shallow sea had occupied this region, and as the sea periodically evaporated, driven by the same warm climate that characterized the late Cretaceous, it deposited thick layers of calcium sulfate on the seafloor. By 66 million years ago, these layers were hundreds of meters thick beneath the shallow water of the platform. When the asteroid struck, it vaporized them directly into the stratosphere in quantities that have been estimated at 100 billion tons of sulfur dioxide and sulfuric acid aerosols. 100 billion tons. The aerosols persisted in the stratosphere because there is nothing at stratospheric altitudes to remove them quickly. Below the stratosphere, rain washes aerosols out of the atmosphere within days to weeks. Above it, in the calm, rain-free stratosphere, particles can persist for years. The Chicxulub sulfate aerosols spread globally on stratospheric winds within weeks and remained for an estimated 2 to 10 years, forming a persistent veil that reduced incoming solar radiation by an amount sufficient to halt photosynthesis across large areas of the Earth's surface. Without photosynthesis, the food chain collapses from the base upward. Phytoplankton in the ocean surface die. Marine food webs, dependent on phytoplankton, lose their foundation. On land, plants die. Herbivores starve within months. Carnivores, dependent on herbivores, follow within a year or two. The pattern in the fossil record, cross-referenced across dozens of KPG boundary sites on every continent and in every ocean basin, is consistent with this sequence. The animals that survived tended to share a set of characteristics: small body size, which means lower absolute food requirements; generalized diet, which means flexibility when preferred food sources disappear; the ability to enter dormancy or torpor; seeds or eggs in the soil that can wait out years of cold and darkness. These characteristics describe, almost exactly, the profile of the mammals that eventually expanded to fill the vacated ecological space. They also describe insects, and freshwater fish, and the seed-bearing plants whose buried seeds would outlast the darkness, and the birds which are dinosaurs whose generalized feeding behaviors and relatively small body sizes allowed many lineages to persist. They do not describe a 15-ton sauropod. They do not describe the specific ecological requirements of Tyrannosaurus rex, which needed hundreds of kilograms of food per week and was unlikely to have had significant fat reserves. They do not describe the herd animals, the hadrosaurs, the ceratopsians whose reproduction was tied to seasonal vegetation that had ceased to exist. The killing mechanism was not the explosion. It was the sulfur, and the sulfur came from the Yucatan. And the Yucatan was struck because the Earth had rotated to present it to the incoming asteroid at that particular moment. 13 minutes. The records do not show what determined the timing. They show only the result. The result was the end of one world, and the slow, cold, dark beginning of the one that followed. It is worth pausing on the oceans, because the marine record at the KPG boundary is in some ways more complete than the terrestrial one. Marine sediment accumulates continuously across the entire ocean floor. There is no equivalent to the terrestrial problem of erosion, of fossilization requiring improbable conditions, of entire regions that leave no record at all. The chemical and biological record in ocean cores from every major basin tells the same story from different vantage points. The surface ocean, the photic zone, the upper 100 to 200 meters where sunlight penetrates and photosynthesis occurs, collapsed within a year of the impact. This collapse is recorded in the carbon isotope ratios of sedimentary carbonates. Photosynthesizing organisms preferentially incorporate the lighter carbon isotope into their tissues. When they flourish, the surrounding water becomes isotopically heavier. When they disappear, the fractionation stops. At KPG boundary horizons in ocean cores from the Pacific, the Atlantic, the Indian Ocean, and the Southern Ocean, the carbon isotope signature shows an abrupt collapse from a high productivity signal to one consistent with near total failure of surface photosynthesis that is simultaneous, globally, within the resolution of the dating. The organisms that disappeared were the calcareous nanofossils and the planktonic foraminifera microscopic, shell-building creatures that formed the foundation of the late Cretaceous marine food web. Their shells, when the organisms died naturally, sank to the ocean floor, carrying with them the carbon they had incorporated from surface waters. This biological pump, the transfer of carbon from the surface ocean to the deep ocean through the sinking of biological material, is one of the principal mechanisms by which the ocean absorbs carbon dioxide from the broad atmosphere. When the pump failed, ocean chemistry began to shift in ways that compounded the surface effects of the sulfate aerosols. Above the boundary layer, in the early Paleocene, the nanofossils and foraminifera reappear, but in reduced diversity, dominated by small, fast-reproducing opportunist species tolerant of stressed conditions. The rich, late Cretaceous marine communities took millions of years to reconstitute. The ocean told the same story as the land, in a different script, at the same moment, for the same reason. The impact direction is documented in the asymmetry of the crater itself. When an object strikes at an oblique angle, the crater it leaves is not perfectly circular. The ejecta field is not symmetrically distributed. The uprange side of the crater shows different structural features than the downrange side. By measuring these asymmetries precisely using data from seismic surveys, drill cores, and gravitational mapping, it is possible to reconstruct the direction and approximate angle of approach. In 2020, a study published in Nature Communications by Gareth Collins and colleagues used three-dimensional computer simulations of the impact to match the structural features of the Chicxulub crater to modeled impacts at varying angles, directions. They tested approaches from multiple compass headings at angles ranging from 15 degrees above horizontal to near vertical. The best fit to the observed crater asymmetry was an approach from the northeast, at an angle of 45 to 60 degrees above horizontal. In impact physics, the angle of impact has profound consequences for how the energy is distributed, and specifically for how much material is thrown into the upper atmosphere. A near-vertical impact, one coming straight down, excavates deeply and ejects material primarily upward and downward. Much of the ejecta falls back near the crater within minutes. A very shallow, grazing impact distributes energy laterally across a wider area, but vaporizes relatively less target material and launches less of it into high-altitude trajectories. The intermediate range, roughly 45 to 60 degrees from horizontal, is, in the words of Collins and his co-authors, the angle most efficient at maximizing the volume of material launched into the upper atmosphere on long-duration ballistic trajectories, available to encircle the globe before descending. Only approximately 1/4 of all impacts occur within this angular range. 3/4 arrive too steeply or too shallowly to achieve this particular combination of material vaporization and atmospheric injection. The 45 to 60 degree window is not just globally efficient. It interacted specifically with the Yucatan platform in a way that compounded the sulfur injection. An asteroid striking the anhydrite layers of the Yucatan at a near vertical angle would have vaporized the rock directly beneath the impact, and much of the sulfur in that rock would have been thrown downward or laterally at low angles, remaining close to the surface. An impact at 45 to 60 degrees, coming from the northeast, would have vaporized a column of rock that extended at an angle beneath the platform, excavating a larger volume of anhydrite-bearing material and projecting the resulting vapor into the stratosphere on an asymmetric plume biased toward the southwest, toward the deep ocean, away from the continental interior, but at exactly the altitude and velocity needed for global stratospheric dispersal. The downrange direction mattered too. The ejecta plume from a northeast to southwest impact was directed over the open Pacific. This meant that the heat pulse from re-entering ejecta was concentrated over the Pacific and the Western Hemisphere rather than over land. The fires it ignited were real and documented charcoal layers in the KPG boundary sediments of North America are particularly thick. But a different approach direction might have concentrated the re-entry heat pulse over Eurasia or Africa instead. The biomes in those regions might have been affected differently. The survival patterns might have been different. The asymmetry extended to the aerosol distribution as well. Atmospheric modeling of the impact suggests that the sulfur plume, biased toward the southwest by the angle of impact, distributed itself most densely over the tropical regions of the Pacific and Atlantic, precisely where the ocean surface temperatures were highest and where the thermal contrast driving atmospheric circulation was greatest. This positioning may have maximized the disruption to the global climate system. The asteroid arrived from the right direction. It arrived at the right angle. The combination of these two factors, the angle that maximized atmospheric injection, directed toward the geography that maximized climate disruption, produced the specific impact winter that followed. Either factor alone, slightly altered, would have produced a different outcome. Together, they compounded. In the records, this kind of compound coincidence is difficult to hold in mind without it becoming uncomfortable. The discomfort is not a product of imagination. It is a product of the math. The Kaiho and Oshima study quantified one dimension of this coincidence, the 13% probability associated with the target rock. No comparable study has yet quantified the combined probability of impact location, angle, direction, season, and prior geological history, all simultaneously producing the conditions necessary for a global mass extinction. The calculation, if it were performed, would produce a very small number. The records have not yet produced it. They have produced, instead, the crater asymmetric, 180 kilometers wide, buried under a kilometer of younger rock, and the instruction to draw whatever conclusions follow from that asymmetry. There is a thought experiment that geologists and impact specialists sometimes use when discussing these coincidences, not for publication but in conversation. It goes like this. Take the Chicxulub impactor and alter one of its properties slightly. Move the arrival time by 20 minutes in either direction. Change the approach angle by 15 degrees. Change the target rock from anhydrite to basalt. In any of these cases, what follows is not a mass extinction. It is a very large explosion, and fires, and tsunamis, and some years of climate disruption followed, over decades or centuries, by recovery. The dinosaurs survive. The mammals remain small. The long Mesozoic continues. The thought experiment is not a rigorous calculation, but it captures something real. The margin between catastrophe and continuity was narrow. The properties of the impact did not need to be different by much. They needed only to be different by the kind of margin that geological chance routinely produces: a different orbit, a different entry angle, a different patch of seafloor. The margin was not the difference between a near miss and a direct hit. It was the difference between a direct hit that killed everything and a direct hit that changed very little. 1/4 of all angles, 13% of all locations, 1 day in 365. The numbers are independent, their product is small. The detail of the season was recovered slowly, and from a source nobody anticipated: the internal structure of fish bones. Fish, like trees, accumulate material in their hard tissues at rates that vary with the seasons. In trees, this produces annual rings, visible in cross-section, that alternate between dense, dark, late wood laid down in autumn and lighter, porous, early wood laid down in spring. In fish, the analogous structures are found in the bones and in the otoliths, small, dense, calcium carbonate structures in the inner ear that help the fish maintain balance and orientation in water. Otoliths grow continuously throughout a fish's life, adding material in concentric layers. The chemistry of each layer reflects the water temperature and food availability at the time it was deposited, which varies seasonally. The spacing and chemistry of the outermost layer, the last thing added before the fish died, can be read to determine the season of death. The fish in the Tanis bed were sturgeon and paddlefish, both long-lived species that accumulate many years of growth records in their bones and otoliths. By examining the outermost growth material in Tanis specimens under high-resolution microscopy and mass spectrometry, paleontologists could determine not just that these fish died, but approximately when in the annual cycle they died. In 2021, De Palma's team published a paper concluding that the fish had died in spring. They based this on the isotopic composition of the outer growth layers, specifically the ratio of oxygen isotopes, which reflects water temperature and correlates with season. In 2022, an independent team led by Melanie During of Uppsala University published a parallel analysis in the journal Nature. During's team used a different methodological approach: high-resolution carbon isotope measurements of the daily growth increments in paddlefish dentary bone, calibrated against modern paddlefish seasonal growth data, and arrived at the same conclusion. The fish had died in Northern Hemisphere spring, specifically in a period consistent with late March through June. The two teams used different methods. The agreement between them was striking. The relationship between the two teams, however, was not. During and her colleagues filed a formal complaint of research misconduct against De Palma with the University of Manchester. The 2023 investigation that followed found evidence of poor research practices in some of his published descriptions of the site, while not finding fabrication. The springtime conclusion itself, the result that both teams reached independently by different methods, was not among the disputed findings. The spring detail matters for reasons that go beyond the aesthetic appeal of a spring morning at the end of the world. In the Northern Hemisphere, spring is the season of maximum biological investment in reproduction and in the most vulnerable life stages. Dinosaur nesting sites, preserved in several formations including the Gobi Desert and the Two Medicine Formation of Montana, show clutch brooding behavior in theropods. Eggs were being laid. Nests were being attended. Hatchlings were emerging. The biological energy of the ecosystem was maximally concentrated in its least resilient forms, the small, the unhatched, the animals that required weeks or months of parental feeding before they could fend for themselves. An impact that removes parents within hours of the breeding season removes not just the adults, but the entire breeding investment of that year. Hadrosaurs appear, from trackway and skeletal evidence, to have nested colonially in large aggregations, as modern colonial nesting birds do. If an impact in spring disrupted a nesting colony, the losses would have extended beyond the individuals present to include the eggs and hatchlings of the entire breeding season. The absence of that season's young would have, in a species with a multi-year time to sexual maturity, compounded the population decline in subsequent years, even in the absence of further catastrophe. In the Southern Hemisphere, the same impact arrived as autumn. Southern Hemisphere populations of many species would have been in a physiologically different state. Fat reserves at or near their peak, reproductive investment winding down for the season rather than at maximum, young of the year already at least partially independent. Some of the southern lineages were beginning to enter seasonal dormancy or reduced activity states. The asymmetry between hemispheres may have shaped the asymmetry of the extinction in ways that are still being traced in the fossil record. Some researchers have noted that several lineages known to have survived the KPG boundary-specific turtle families, certain mammal groups, some lizard lineages show early Paleocene representatives concentrated in southern latitudes or in southern hemisphere fossil beds. The pattern is consistent with a hypothesis that seasonal state at the moment of impact contributed to survival probability. It has not been conclusively demonstrated, but the evidence is accumulating. If the impact had occurred in autumn in the Northern Hemisphere, the same asteroid, the same location, the same energy release, the same sulfur injection, the specific lineages that perished and those that survived might have been different. The world that followed might have inherited a different set of survivors. Not necessarily a world with dinosaurs, the impact winter itself was not seasonally dependent, but a world with a different array of the species that outlasted the darkness. A different starting set for the Paleocene recovery. Different evolutionary outcomes. The records do not show what that world would have contained. They show only that the timing, in addition to everything else about the impact, was wrong. There is another dimension to the seasonal argument that the records touch on less directly. In the late Cretaceous, the timing of seasons was different in specific ways from what we experience now. The obliquity of the Earth, the tilt of its axis relative to its orbit around the Sun, oscillates over long cycles, and 66 million years ago, it was within a range that produced seasons broadly comparable to those of the present, perhaps slightly more extreme at high latitudes. The seasonal cycle of the western interior Seaway region, where the Hell Creek fauna lived, would have produced warm, wet summers and cooler, drier winters, not dramatically different from what a temperate continental interior experiences today. The nesting season for most dinosaur lineages in this region appears from trackway and skeletal evidence to have begun in late winter or early spring, when temperatures rose and the first vegetation of the year became available. This is the pattern in most modern archosaurs, from crocodilians to birds, and there is no reason to expect the non-avian dinosaurs were markedly different. A spring impact would have found nesting not only underway, but at its most active phase. Clutches being incubated, hatchlings emerging, parents maximally invested in offspring that could not yet survive independently. The long-term population consequences of the loss of a single breeding season in a species with a multi-year time to first reproduction are not trivial. A large-bodied dinosaur that required 5 to 10 years to reach reproductive maturity and that lost its breeding cohort in the spring of 66 million years ago would have had no replacement cohort. The individuals that survived the initial catastrophe faced a future without the next generation. Even in the absence of further mortality, a population that fails to reproduce for a single year and then faces years of food stress is unlikely to recover. The spring was not merely a detail, it was a mechanism. The record carries it quietly, in the chemistry of bones that no one thought to look at in this way until the early 21st century, in a bed in North Dakota that no one knew existed until 2012. The dinosaurs, by 66 million years ago, were not at their peak. They were not, in several significant respects, even thriving. A 2021 study published in Nature Communications by Fabienne Condamine and colleagues analyzed the diversification rates of every well-documented non-avian dinosaur lineage across the final 10 million years of the Conamine. Cretaceous. The methodology was phylogenetic, using the known evolutionary relationships between species and the dating of their fossil records to calculate rates at which new species were appearing. Speciation and existing species were disappearing, extinction, and different lineages at different times. Their finding was unambiguous. Across most major non-avian dinosaur lineages, net diversification rates had been declining for approximately 10 million years before the asteroid impact. The rate at which new species were appearing had slowed. The rate at which species were going extinct had risen. The lineages were not yet collapsing, they were still diverse, still ecologically dominant, still filling their niches. But the trend was negative, and it had been negative for a geological epoch. Some lineages showed this decline more clearly than others. Ceratopsians, the horned dinosaurs, and hadrosaurs showed the clearest signal of declining diversification. Theropods, the bipedal predatory lineage that includes Tyrannosaurus, showed a mixed picture. Some groups in decline, others stable. The sauropods, the long-necked giants that had dominated the earlier Jurassic, had already been reduced in diversity and were absent from many of the late Cretaceous ecosystems of Laramidia. The leading hypothesis for the cause of this pre-impact decline is the Deccan Traps, a series of massive volcanic eruptions in what is now Western India that began approximately 66.5 million years ago, continued in pulses for hundreds of thousands of years. The Deccan event was one of the largest volcanic episodes of the past 100 million years. The scale is difficult to convey. The eruptions ultimately deposited basalt flows covering an area of approximately 500,000 square kilometers, to depths of up to 2 kilometers in some places, producing a total volume of roughly 1 million cubic kilometers of rock. For comparison, the largest volcanic eruptions in human history, Tambora in 1815, Pinatubo in 1991, produced fractions of a cubic kilometer of material. The Deccan eruptions released enormous quantities of carbon dioxide and sulfur dioxide into the atmosphere, not in a single catastrophic event, but in a prolonged series of pulses over hundreds of thousands of years. The CO2 caused global warming episodes. The sulfur dioxide caused short-term cooling during the periods of most intense activity. Sea levels fluctuated as the climate oscillated. The warm, stable climate of the earlier Cretaceous became more variable. Shorelines retreated and advanced. Shallow water habitats that had supported particular dinosaur communities expanded and contracted with the sea level changes. The shallow arm of the Western Interior Seaway, which divided North America and supported the ecosystems preserved in the Hell Creek Formation, was already being altered by the end Cretaceous regression, a significant sea level fall that was already underway before the asteroid arrived. The question of whether the Deccan eruptions alone would eventually have caused a mass extinction, given enough time, is unresolved. The consensus view is that they were not sufficient on their own. The extinction they were producing was gradual and incomplete, and many major groups appeared likely to persist. But the stress they imposed on ecosystems meant that those ecosystems were less resilient when the asteroid arrived. The already declining lineages had less redundancy, less diversity, less capacity to recover. The organisms and food webs that survived the first year of impact winter were doing so against a backdrop of ecosystems that had already been weakened. What the records suggest is that the asteroid did not invent the extinction. It accelerated and completed a process that had been building for 10 million years. It compressed into a few catastrophic years, a decline that might otherwise have taken another 10 or 20 million years to produce a comparable biological reorganization. This complicates the alternate history question in a specific way. If the asteroid had missed, if the 13-minute window had placed the impact in the Pacific, instead, the dinosaurs would not simply have continued unchanged. They were already in slow decline. The Deccan eruptions would have continued. The sea level regression would have continued. The ecosystems of the Hell Creek Formation would have continued to change. The specific trajectory of what followed is impossible to reconstruct. But what can be said is that the alternate timeline does not begin from a position of dinosaur stability. It begins from a position of ongoing, multi-million-year stress. Perhaps the decline would have reversed. Conditions change. New species evolve. Lineages that appear to be contracting have sometimes expanded again when conditions shifted. The fossil record contains examples of apparent declines followed by diversification pulses. There is no reason to assume that the trajectory observed in the final 10 million years of the Cretaceous was irreversible. Perhaps it would not have reversed. Perhaps the Deccan eruptions, continued over the following hundreds of thousands of years, would have completed a slower extinction, one that preserved more species at any given moment, but ultimately removed the dominant lineages just as completely, leaving the same vacated niches for the mammals to expand into on a different timescale. The archive does not resolve this question. It documents the trend, and then it documents the impact, and then it documents the boundary, 3 millimeters of iridium-rich clay, in which the answer to the question of what would have happened next was permanently foreclosed. There is a detail about the Deccan eruptions that the records added recently, and that changed how researchers think about the relationship between the volcanism and the impact. A 2020 study in Science found that the asteroid impact itself appears to have intensified the Deccan eruptions. The seismic waves generated by the impact traveling through the Earth's mantle for days appear to have triggered volcanic activity at the Deccan site, dramatically increasing the eruption rate in the months and years that followed. The asteroid, in other words, did not only cause a mass extinction through its direct effects, it also amplified the ongoing volcanic crisis that had already been stressing the biosphere. The picture that emerges is one of a biosphere that was stressed before the impact, struck catastrophically during it, and then further burdened afterward by the volcanic intensification that the impact itself caused. The three effects did not add. They compounded. Each made the others worse. The dinosaurs that survived the initial heat pulse faced the impact winter in ecosystems already weakened by 10 million years of Deccan-driven instability, in a world where the volcanism they had been adapting to was now, in the asteroid's aftermath, accelerating. The file on the end of the Cretaceous is not a simple record of a single cause. It is a record of intersection of several independent processes arriving at the same place at the same time and combining into an outcome that none of them, separately, would have produced. The 13-minute sits at the center of the intersection. In the late 1970s, a Canadian paleontologist named Dale Allen Russell became interested in a question that most of his colleagues considered professionally inadvisable. What would have happened to the dinosaurs if they had not gone extinct? Russell was, at the time, curator of vertebrate fossils at the Canadian Museum of Nature in Ottawa. His career had been distinguished. He had named several dinosaur genera, published influential work on Cretaceous vertebrate faunas, and was regarded by colleagues as a careful scientist with an unusual willingness to address large-scale questions at a time when paleontology was becoming increasingly specialized. One colleague later described him as having a penchant for meta-narrative rarely equaled in these times of increased research specialization. Russell had noticed, in his study of theropod dinosaurs, the bipedal, often predatory lineage that includes Tyrannosaurus, Velociraptor, and their relatives, a consistent trend across the Mesozoic. Relative brain size, measured as the ratio of brain mass to body mass, had been increasing. The trend was not universal and not linear, but across the theropod lineage as a whole, the late Cretaceous representatives showed larger brains, relative to body size, than their Jurassic predecessors. The clearest expression of this trend was a group called the Troodontids, small, lightly built, fast-moving theropods of the late Cretaceous. The most well-known species, Stenonychosaurus inequales, later reclassified under the genus Troodon, was approximately the size of a small ostrich, bipedal, with three-fingered hands showing a degree of grasping capability, large forward-facing eyes indicative of good depth perception, and a brain-to-body ratio that was the highest of any non-avian dinosaur, then known, roughly comparable to that of modern birds, and substantially higher than that of modern crocodilians, which are the closest living relatives of the dinosaurs. Whether its cognitive capabilities match those implied by its brain size is a question the fossil record cannot answer. Brains do not fossilize. Only their containers do. Russell performed a calculation. Using the measured rate of relative brain size increase across the theropod lineage over the last 100 million years of the Mesozoic, and extrapolating that rate forward by 66 million years, the time that had elapsed since the extinction, he projected what a descendant of Stenonychosaurus might look like by the present day. The projection indicated a brain mass in the range of 1,300 grams, comparable to the average human brain. This figure was not arbitrary. It followed from the extrapolation of a measured trend. To support a brain of this size, the body plan would have needed to change. A larger brain requires a larger skull, which in a biped requires a more vertical neck posture, which requires a more upright overall stance, which, combined with the increased cognitive demands of high intelligence, might be expected to produce selective pressure toward greater manual dexterity in the hands. The eyes, already large and forward-facing in Stenonychosaurus, would remain so binocular vision is essential for the precise manipulation tasks associated with high-order cognition. In 1982, Russell co-authored a paper with the model maker Ron Seguin titled Reconstruction of the Small Cretaceous Theropod Stenonychosaurus inequalis and a Hypothetical Dinosauroid. The paper appeared in Sylogis, the research journal of the Canadian Museum of Nature. It included a life-size sculpture made from clay, resin, and paint of a bipedal, large-brained, large-eyed humanoid figure with greenish-brown scaled skin, three-fingered hands, and a smooth, somewhat alien face. Russell called it the Dinosauroid. The paper was peer-reviewed. The science was, by the standards of speculative anatomy, careful. It began from a real fossil, applied a measured trend, and produced a prediction. It did not claim that the Dinosauroid was what would have existed. It claimed that such a body plan was a plausible outcome of the continuation of the documented trend. The reaction in the paleontological community was divided. The criticism that gained the most traction was the accusation of anthropomorphism, that the dinosauroid looked too much like a modified human, that Russell had unconsciously projected a human body plan onto an extrapolated dinosaur rather than following the actual constraints of dinosaur anatomy. A number of subsequent researchers noted that the troodontids retained features: a digitigrade foot, a grasping second toe, a tail that were unlikely to have been lost entirely in a more intelligent descendant, and that a truly derived troodontid would more likely have maintained a partially horizontal posture, using a long tail as a counterbalance, and would have had a skull anatomy quite different from any mammal. The artist and researcher C.M. Koosman, co-author of the Paleontological Art Guide, All Yesterdays, produced an alternative dinosauroid reconstruction that retained these features. A creature that was clearly related to Troodon, clearly more intelligent, clearly further derived, but emphatically not a green human. Koosman's version had a beak, a long tail, a crouched stance, and eyes set more laterally than Russell's model, a being that might have been highly intelligent, but whose intelligence would have found expression in a body plan shaped by 165 million years of evolution, quite different from the line that produced us. The central premise of Russell's 1982 paper, that the trend toward larger relative brain size in theropods, if continued, would have produced some form of high intelligence, has never been formally refuted. The math is sound. The fossil trend is real and measured. The conclusion, if uncomfortable, is mathematically supported. What is disputed is the specific form the intelligence would have taken, not whether it would have appeared at all. What Russell was suggesting, and what subsequent researchers have built on, is that the asteroid did not merely end the dinosaurs. It ended a possible future in which the theropod lineage developed minds, perhaps radically different minds, organized in ways we cannot predict from the fossil record, expressed in bodies that would not look like us, but minds nonetheless. Russell continued working on questions of intelligence and evolution throughout his career. He contributed to discussions within the Search for Extraterrestrial Intelligence program, exploring whether the emergence of intelligence was convergent enough that it might appear reliably on other planets. His later book, Islands in the Cosmos, hinted at a worldview in which certain outcomes, intelligence, complexity, the emergence of beings capable of asking questions, were destinations toward which evolution tended, given sufficient time and stability. Dale Russell died in December 2019. He did not live to see the 2021 paper by Condamine confirming the pre-impact decline, or the 2022 Nature paper establishing the spring season, or the refined modeling of the 13-minute window. He did not live to see the full extent to which the records confirmed that the impact's extinction-causing properties were contingent and narrow. The dinosauroid model sits in storage at the Canadian Museum of Nature in Ottawa. It is not on permanent display. Those who have seen it describe it as unsettling, not because it looks alien, but because it looks almost familiar. A being shaped by 66 million years of evolution in a different direction, but evolution toward a destination that, by a different path, we also reached. The records preserve the bones of what it came from. They cannot preserve what it might have been. There is a framing of the Kapig story that is common in popular accounts and misleading in a specific way. It describes the small mammals of the late Cretaceous as having been waiting in the wings, patient survivors biding their time through the long age of dinosaurs, ready to emerge the moment the constraint was lifted. The framing implies a kind of inevitability that mammals were always going to take over, that they were always destined to be the dominant terrestrial vertebrates, that the dinosaurs were only temporarily in the way. The record does not support this. The mammals of the late Cretaceous were not waiting. They were occupying the ecological roles available to them in a world dominated by other animals. They had been doing so for over 150 million years, longer than the non-avian dinosaurs themselves had been around. They had not been constrained by some external force, preventing them from becoming large. They had been living in a world that provided no selection pressure to become large, because the large animal roles were filled and well defended and had been filled for longer than any mammal's evolutionary lineage had existed. The mammals of the late Cretaceous were small, because small was what the ecosystem had room for. They were nocturnal because the daytime, in most of their habitats, belonged to animals that ate them. They were generalists eating insects, seeds, small reptiles, eggs, whatever was available, because specialization for any particular resource risked direct competition with a dinosaur lineage that was better at it. Reshaped robustus, at roughly 14 kilograms, was the exception and the outlier. Fossils of Reshaped from the early Cretaceous of China have been found with the remains of juvenile dinosaurs in the stomach region, the earliest direct evidence of a mammal eating a dinosaur. 14 kilograms was as large as a Cretaceous mammal got. It achieved this size in a specific ecological context, in a region and period where the dinosaur fauna happened to include a niche it could exploit. It was not a harbinger of mammalian dominance. It was a local anomaly. The eutherian mammals, the placental group that would, after the extinction, give rise to all living mammal orders, including our own, were, in the late Cretaceous, unremarkable in their size and diversity. The best documented late Cretaceous eutherian is a small animal called Purgatorius, found in the earliest Paleocene sediments of eastern Montana, which may also have a Cretaceous record depending on how certain fragmentary teeth are interpreted. It was approximately the size of a small rat. It probably ate insects and plant matter. Its distinguishing feature, what separates it from its contemporaries and marks it as a eutherian rather than a metatherian or multituberculate, is in the structure of its teeth, not in anything behaviorally or ecologically remarkable. What happened after the impact was not the emergence of a group that had been waiting for its chance. It was the rapid adaptive radiation of a set of surviving lineages into a world that had suddenly, catastrophically, become empty of its dominant occupants. The ecological niches that the dinosaurs had filled, large browser, large predator, medium-sized omnivore, small insectivore, aerial hunter, did not disappear with the dinosaurs. They persisted as structural features of the environment, as resources to be harvested, as roles to be filled. Natural selection, operating on the surviving mammal lineages, filled them with whatever raw material was available. Within 10 million years of the KPG boundary, mammalian body sizes had increased by several orders of magnitude. Pantodonts, condylarths, and other early Paleocene groups achieved sizes of several hundred kilograms. Within 30 million years, all of the modern mammalian orders had appeared in the fossil record. Within 40 million years, primates, the order to which humans belong, had diversified from small, insectivorous, arboreal ancestors into a range of forms occupying different ecological niches in tropical and subtropical forests. The primates are relevant here not merely as our ancestors, but as an example of what ecological release can produce when the conditions are right. Primates, in their early evolution, were not notable among mammals for their size or their ecological impact. What distinguished them was a suite of traits: forward-facing eyes, grasping hands, and relatively large brains for their body size that may have been adaptations to an arboreal, visually demanding foraging lifestyle in tropical forest canopies. These traits turned out, over the following tens of millions of years, to be highly general in their usefulness. They could be applied to a wide range of ecological roles. They were, as evolutionary investments, extraordinarily versatile. If the asteroid had missed, if the 13-minute window had placed the impact in the Pacific, if the sulfur had not reached the stratosphere in extinction-causing quantities, if the dinosaurs had continued, the mammals would not have undergone this radiation. The niches would have remained occupied. The selection pressure toward larger body sizes and more complex behaviors would have been absent or greatly reduced. The primates might have appeared, or a small, arboreal, insectivorous lineage with a similar adaptive profile might have appeared. but there would have been no ecological pressure driving them toward large body size or toward the expansion into a diverse range of habitats that produced, over millions of years, the particular evolutionary trajectory that led to us. This is the second uncomfortable conclusion embedded in the record. The first was that intelligence might have evolved in the dinosaur lineage, given another 66 million years. The second is that intelligence might not have evolved in the mammalian lineage at all, not because mammals were incapable of it, but because the ecological space in which mammalian intelligence emerged was a space created by the asteroid. And in the asteroid's absence, that space would not have existed. The two conclusions sit in uneasy proximity in the literature. They cannot both be fully true simultaneously. If intelligence is convergent, if any biosphere with enough time and complexity eventually produces it, regardless of which lineage it comes from, then the question is not whether intelligence would have appeared, but in which lineage. If intelligence is contingent, if it required the specific conditions of the Cenozoic, the specific ecological release of the post-KPG world, the specific evolutionary history of the primates, then the asteroid was not merely a detour around the emergence of intelligence, it was its cause. The records of Earth cannot adjudicate between these possibilities. They show only that intelligence followed the asteroid. Whether it would have followed by a different path, in a different lineage, in the asteroid's absence, this is the question that the 3 millimeters of iridium clay at the KPG boundary does not answer. What it does answer is simpler and stranger. It answers the question of what it took. It took 13 minutes. It took 1/4 of all possible impact angles. It took one planet in 13. It took a spring morning. It took 10 million years of prior decline. It took 150 million years of waiting, patient, small, nocturnal, eating insects in the dark. It took all of these things, in combination, at the same time. The record presents this without comment. It has no other way of presenting it. What the record also contains, less often remarked upon, is the evidence of what the mammals did with the space they were given. The radiation of placental mammals in the Paleocene and Eocene is among the fastest large-scale diversifications in the fossil record. Within the first 10 million years after the boundary, animals the size of small horses had appeared. Within 20 million years, the first whales had returned to the sea, descendants of four-legged terrestrial mammals that had entered coastal waters and, over 10 million years, lost their hind limbs and developed the body plan we recognize. Within 40 million years, the first apes had appeared. This was not slow, gradual change of the kind associated with undisturbed, stable ecosystems. This was the explosive filling of empty ecological space, as fast as natural selection could manage. The vacancy left by the non-avian dinosaurs was not merely ecological, it was cognitive. The late Cretaceous dinosaurs had occupied, in their neural architecture, a space that was complex and capable enough to produce, in the surviving avian lineage, the corvid intelligence and the parrot intelligence that we observe today. In the non-avian lineage, that space was cut short. The Paleocene mammals that inherited the world were, neurologically, starting from a smaller base, but they were starting into an empty world, with every ecological and cognitive niche available. Selection pressure for intelligence, in a complex, competitive, rapidly changing post-extinction world, was high. The primate brain, which eventually produced this account of what ended the Cretaceous, is not the inevitable product of evolution. It is one solution among many that the empty post-KPG world could have produced. The records show it happened. They do not show it was the only way. There is a category of question that the fossil record cannot answer, and the question of what dinosaur intelligence would have become falls within it. Bones preserve. Brains do not. The size of a brain can be inferred from the dimensions of the cranial cavity that once contained it, and paleontologists have used latex and silicone endocasts, casts made from the interior surface of fossilized skulls to map the external shape of dinosaur brains with reasonable accuracy. What the endocasts cannot preserve is the internal organization of the brain tissue, the folding of the cerebral surface, the relative development of different regions, the density and connectivity of neural pathways, the distribution of neurochemicals that mediate behavior. For the purposes of estimating cognitive capability, these internal details matter more than overall size. Human brains and dolphin brains are similar in absolute mass. Crow brains and primate brains are, relative to body size, comparable in their ratio, but the internal organization differs significantly, and the differences in organization produce differences in cognitive capability that cannot be predicted from size alone. What can be said is this: the brains of late Cretaceous theropods were, by the standards of non-avian reptiles, large. The endocast evidence for Troodon and related troodontids shows a brain with developed olfactory lobes, large optic lobes consistent with the large eye sockets of the skull, and a cerebral region that is, relative to brainstem, larger than in crocodilians and more comparable to that seen in modern birds. This comparison to birds is significant because birds are the living dinosaurs, the direct descendants of theropod ancestors, through a lineage that diverged from the non-avian theropods in the Jurassic and survived the KPG extinction. The cognitive capabilities of modern birds are, in some groups, remarkable. Corvids, crows, ravens, jays, magpies are capable of multi-step tool use, of planning for future events, of recognizing individual human faces and remembering them across years, of communicating specific warnings about specific predators, and of what researchers have cautiously termed episodic memory, the ability to recall specific past events in terms of what happened, where, and when. Ravens have been observed making and keeping social commitments and reacting to violations of those commitments. New Caledonian crows manufacture and use hooked tools to extract food from locations they cannot reach directly. African gray parrots, tested with formal cognitive assessments, have demonstrated performance comparable to that of young children on tasks involving symbolic reasoning and zero-concept understanding. These are birds. Birds that evolve from theropod ancestors. Birds whose last common ancestor with Troodon lived in the Jurassic and was, in cognitive terms, far less developed than either of its descendants. The avian lineage, over the subsequent 150 million years, arrived at these cognitive capabilities through its own evolutionary path. The non-avian theropod lineage, had it been given the same duration, might have arrived somewhere different, or somewhere similar. The record cannot say. What it can say is that the question of dinosaur intelligence is not merely the speculation it might appear. It is grounded in measured trends, in comparative neuroscience, in the documented cognitive capabilities of the lineage's surviving representatives. Russell's 1982 paper was not the last word. It was the first rigorous formulation of a question that the record itself, by its incompleteness, keeps open. The dinosauroid model sits in storage. The records of what the troodontids might have become were buried 66 million years ago, in the same iridium clay that caps every KPG boundary site. They were not preserved. The record ends there, and what comes after is inference, extrapolation, and the stubborn silence of 3 millimeters of clay. There is one further dimension to the silence. The question of whether dinosaurs would have developed intelligence is, in its deepest form, a question about what intelligence is for. Mammalian intelligence, primate intelligence, specifically appears to have developed in the context of complex social environments, of long-term relationships with individually recognized others, of deceptive and cooperative behavior, of the need to model the mental states of competitors and allies. Social complexity appears to be a strong driver of neural complexity. The primates with the largest relative brain sizes tend to live in the largest, most socially complex groups, and the evolutionary transition to still larger brains in the hominin lineage tracks the emergence of increasingly complex social structures. Would the troodontids, or their descendants, have developed the kind of social complexity that drives brain expansion in primates? The fossil record cannot answer this. Behavior does not preserve. Whether Troodon hunted cooperatively, whether it had extended social bonds, whether it cared for young past the stage of hatching, these questions remain open. What is preserved is the brain case, the eyes, the hands. The social life that those features were embedded in is gone. It is one of the stranger silences in the record. The most important question about the most consequential event in the last 100 million years of vertebrate evolution is not one the fossils can answer. They can only present the brain case and the iridium clay above it and the changed world above that. What happened in between, what was lost, what might have grown from it, is a record that was never made. It is worth, at this point in the record, returning to the central figure. 13 minutes. The figure is specific enough to be unsettling. 13 minutes is the duration of a moderately long telephone call. It is the time required to boil water for pasta, or to walk a kilometer at a comfortable pace, or to read through the first pages of an evening's book before deciding whether to continue. It is the gap between two trains on a reasonably well-managed urban transit system. It fits inside the margins of a typical commute. 13 minutes determined whether the dominant terrestrial vertebrate lineage of the preceding 165 million years would continue or end. It determined whether the mammals, small, nocturnal, occupying the margins of the dinosaur world for a period longer than the entire Cenozoic, would have ecological space to expand or not. It determined, as a downstream consequence of these two things, whether a particular branch of the primates would develop, over the following tens of millions of years, the neural architecture that currently underlies the ability to ask any of these questions. The records do not show what determined the timing. The asteroid's trajectory was set by gravitational interactions stretching back, perhaps, to the formation of the solar system. Earth's rotation rate was set largely by the moon-forming impact. 4.5 billion years earlier, a collision between the proto-Earth and a Mars-sized body that knocked the planet onto its current axial tilt and sent enough material into orbit to form the moon. The rotation rate the moon-forming impact produced has been slowly decreasing ever since, as tidal interactions with the moon transfer angular momentum away from Earth. 66 million years ago, the day was approximately 30 minutes shorter than it is now. This small difference in rotation rate means that any given point on the Earth's surface was at a slightly different position at any given moment compared to what the calculation for a modern day would yield. The precise 13-minute figure depends on the precise rotation rate of the Cretaceous Earth. The asteroid's trajectory and Earth's rotation rate were set by processes separated by billions of years and operating by completely independent mechanisms. They had no relationship to each other. They intersected once, on a spring morning 66 million years ago, at a shallow sea off the northern Yucatan Peninsula. There's a concept in physics called fine-tuning, used most prominently in cosmology to describe the apparent precision of the fundamental physical constants, the strength of gravity, the mass of the electron, the energy density of the vacuum, whose values, if altered by even small amounts, would produce a universe in which stars cannot form, or atoms cannot exist, or chemistry cannot operate. The fine-tuning problem is the observation that the universe seems configured very precisely for the existence of complex structures, and the question of why this is so does not have a settled answer. The end of the Cretaceous was not fine-tuned in this sense. It was a contingent event, not a fundamental one. No physical constant was at stake, but it had, in its own narrow and local way, a similar character, a set of conditions that needed to align, each within a specific range, for the outcome to be what it was. The target rock, the angle of impact, the time of day, the season, the prior geological history of the target region, the prior evolutionary history of the affected lineages. These are not physical constants, but they are, in the record, all present, all correct, all aligned. The records do not show what, if anything, should be concluded from this alignment. They show the alignment, and they show what followed from it, and they leave the inference to whoever is reading them. The Tanis bed preserves the first 13 minutes. The rest of the record, the iridium layer, the fern spore horizon, the sudden absence of non-avian dinosaur fossils above the boundary preserves what followed. The inference about what it all means remains, at the moment, unrecovered. What the record returns to, when all the technical analysis is set aside, is a question of scale, not the scale of the energy or the scale of the extinction, but the scale of the margin. The difference between the world that existed and the world that followed was not decided by a centuries-long process, or a million-year slow change, or even a decades-long cascade of consequences. It was decided by a fraction of a planetary rotation. 13 minutes. The time it takes the Earth to turn 325 kilometers. The Tanis site, specifically, is a record of what 13 minutes looked like from the ground. The seismic waves arrived in 10 minutes. The spherules began arriving within hours. The fish died in the Seiche surge, in that window, and were buried, and were preserved. The leg of the Theslosaurus was buried before the ligaments had time to decay. The record was made in the interval between the impact and the arrival of the longer-term consequences in the first chapter of the story, before the darkness settled. There is something in this that resists ordinary description. The Tanis site is not a memorial. It is not a monument. It is a riverbed that happened to capture, through an unlikely chain of geological coincidence, the first minutes of the longest reorganization of life on this planet in the past 100 million years. The fish did not know they were dying at the beginning of anything. The Theslosaurus did not know the morning it lived through would be the last one of its kind. The record does not show knowledge. It shows only what happened and when. There are two schools of thought in evolutionary biology about whether intelligent life is an inevitable outcome of evolution on a biosphere or a contingent one. The disagreement between them is unresolved, and neither side has a fossil record sufficient to settle it. What they have, instead, are arguments from the patterns and mechanisms of evolution applied to the problem of intelligence specifically. The convergence school, associated most prominently with the late paleontologist Simon Conway Morris, argues that evolution tends to find the same solutions to ecological problems repeatedly across unrelated lineages. The eye has evolved independently more than 40 times. Wings have evolved in insects, pterosaurs, birds, and bats from entirely different anatomical starting points. Streamlined aquatic body forms have evolved in fish, ichthyosaurs, dolphins, and penguins. Echolocation has evolved independently in bats and in cetaceans. Complex social behavior, tool use, and problem-solving abilities have appeared in the corvids, in the great apes, in elephants, in cetaceans, and in the cephalopods, all of whom are separated by hundreds of millions of years of evolutionary divergence. Conway Morris argued, in his 2003 book Life's Solution, that this convergence is not coincidental. It reflects the fact that the space of viable biological solutions to common ecological problems is not infinite. It is constrained by physics, chemistry, and geometry. Intelligence, in his view, is one of those constrained solutions. A sufficiently useful response to the problem of navigating a complex, competitive environment that evolution, given enough time, will find it independently in lineage after lineage. The particular lineage that achieves it first may be contingent. The achievement itself, he argued, is not. The contingency school, associated most prominently with the late paleontologist Stephen Jay Gould, argues the opposite. In his 1989 book, Wonderful Life, Gould proposed the thought experiment of rewinding the tape of life to the Cambrian explosion, the period approximately 540 million years ago when most major animal body plans appeared in the fossil record, and playing it again. His conclusion was that the outcome would be different every time. The specific trajectory of evolution depends on chance events, mutations, extinctions, chance contacts between lineages that are not repeatable. Intelligence, in Gould's view, is not a convergent solution that evolution reliably finds. It is one of an enormous number of possible outcomes, no more inevitable than any other, and the lineage that achieved it on Earth did so through a chain of contingent events so long that the probability of duplicating it is negligible. The KPG event is, in some ways, the most powerful piece of evidence for Gould's position. A 13-minute difference in the rotation of the Earth, a difference generated by the intersection of two processes with no causal connection, appears to have determined which lineage had the ecological space to develop. Intelligence. This is precisely the kind of contingent, non-repeatable event that Gould's argument requires. In a different run of the tape, the asteroid misses. The contingent difference is less than 1% of a day. But the convergence school has its own response to this. If intelligence is genuinely convergent, then the question of which lineage develops it first is the contingent variable, not whether it develops at all. In the alternate timeline, the one in which the asteroid strikes the Pacific, 66 million years pass. In those 66 million years, the Troodontids, or some descendant lineage, may continue the trend toward larger relative brain size that Russell documented, and may eventually produce something with intellectual capabilities comparable to, or greater than, our own. The convergence argument does not require that intelligence emerge in mammals. It requires only that intelligence emerge in something, eventually, given enough time and a complex enough biosphere. The records of Earth do not adjudicate between these views. Both are consistent with the fossils. The only evidence that might help evidence from other biospheres, other planets, other evolutionary histories has not yet been recovered. We have one data point, one planet, one outcome. The statistics of a sample size of one are inherently limited. What the records do show is that on this Earth, with this evolutionary history, the emergence of intelligence was preceded by one of the most improbable chains of aligned contingencies in the known geological record. Whether that improbability is typical of how intelligence emerges in the universe, or an anomaly in an otherwise common process, is a question the records have not yet answered. Perhaps they will. Perhaps the records of other worlds exist and will eventually be recovered. Perhaps they will show minds that look nothing like ours, built from biology that shares no common ancestor with any life on Earth, having arrived at cognition through completely different mechanisms. Or perhaps they will show nothing, a universe in which the 13-minute window is rarely aligned, in which the asteroid almost always misses, in which the dinosaurs almost always persist, and intelligence almost always waits. The records are silent on this point. There is a related question that has gained prominence in recent decades, one that connects the Cretaceous record to a much larger question about the distribution of intelligence in the universe. The Fermi paradox, the observation that the universe appears large and old enough to have produced many civilizations, and yet no evidence of any has been detected, has several proposed resolutions. One of them, sometimes called the rare Earth hypothesis, holds that the conditions that produced intelligent life on this planet were so improbable that they are unlikely to have been replicated elsewhere. If the 13-minute window is one of those conditions, and if similar chains of aligned contingencies characterize the emergence of intelligence wherever it occurs, then the universe may be very old and very large and very quiet, filled with planets where the asteroid struck the Pacific, where the dinosaurs persisted, where the mammals remained small. Another resolution holds that intelligence is common, but that the timescales and the physical manifestations of intelligence elsewhere are so different from ours that we do not recognize them or cannot detect them with our current methods. The cephalopods provide a modest terrestrial example of this. Octopuses have developed substantial problem-solving capability, tool use, and learned behavior through a neural architecture completely different from the vertebrate brain distributed through their arms rather than centralized in a skull. Developed independently over a lineage separated from the vertebrate line by more than 500 million years. Their intelligence is real. It is also, by the standards of vertebrate intelligence, alien. It is organized differently. It has different strengths and different limitations. It would not build a radio telescope. The records of Earth, in this way, contain a quiet argument for both sides. The contingency of mammalian intelligence and the convergence of cognitive capability in lineages that are not mammalian at all. The argument has not been settled. Perhaps it will not be, from the evidence available on a single planet. The Tanis bed, for all the specificity of what it preserves, does not show certain things. It does not show the moment of impact that occurred 2,800 kilometers to the south, in a region now buried beneath a kilometer of ocean sediment and only accessible through deep drilling. The impact itself left no fossil record at the Yucatan site in the conventional sense. The temperatures and pressures involved were too extreme for organic material to survive. It does not show the impact winter. The aerosols that spread globally over weeks and months produced their effects on a timescale longer than any individual fossil deposit can record. The record of the impact winter lies instead in a different kind of evidence. The sudden shift in pollen types that appears at KPG boundary sites around the world, where conifer and flowering plant pollen abruptly gives way to fern spores, a pattern consistent with the dominance of ferns, which are among the most resilient colonizers of devastated landscapes, in the years immediately following the event. It lives in the charcoal layers that appear in KPG boundary sediments on every continent, and in the carbon isotope anomalies that record the collapse of marine photosynthesis. These are not dramatic. They are centimeters of changed chemistry in rock that requires laboratory analysis to read. It does not show what happened to the survivors. The first 100,000 years of the Paleocene, the period immediately following the KPG boundary, is one of the most poorly documented intervals in the entire Cenozoic fossil record. The conditions that favored preservation in the preceding Cretaceous had changed. The environments that produced the Hell Creek Formation were altered. The lineages that survived were small, burrowing, and had low preservation potential. The record of the recovery is fragmentary precisely because the survivors were the kinds of animals that rarely become fossils. What Tanis shows is a single moment, a morning preserved with unusual completeness, because of an unusual set of depositional conditions. A seismic surge that concentrated fossils in a specific bend of a river valley. The right water chemistry for silicification and phosphatization to preserve soft tissues in some specimens. The right sediment grain size for rapid burial. The right rate of subsequent burial by fine sediment to seal the deposit before erosion could reach it. The conditions that produced Tanis were, themselves, improbable. Most of the spring morning of 66 million years ago left no record at all. The animals that died in the open, on the plains, on the hillsides, in the forests, their remains were scattered, weathered, and recycled. The vast majority of the death that occurred that day, in North America alone, produced no fossil whatsoever. Tanis is a survivor of that death, a fragment of a morning preserved by a chain of geological coincidences, no less improbable in their own way than the chain of coincidences that produced the morning itself. The boundary between the world that was and the world that followed is approximately 3 millimeters thick in the rock at Tanis. 3 millimeters of iridium-bearing clay, deposited over months and years as the global ejecta settled. Below it, the Cretaceous, fish, dinosaur bones, plant material, the record of a world in its last moments. Above it, the Paleocene, different fossils, smaller animals, changed pollen, the record of a world that was beginning something it did not yet know it was beginning. Geologists and paleontologists can pick up a core sample from a KPG boundary site and hold it in their hands 3 millimeters of boundary between two worlds, between the longest continuous dominance of any terrestrial lineage and the slow, cold dawn of the age that followed. The weight of the core is negligible. What it contains is not. What TANIS does not show, and what the global record only partially shows, is the decade after the impact. The decade after the iridium layer settled. The decade in which the survivors, small, nocturnal, burrowing, dormant, generalist, were navigating a world in which most of the species they had evolved alongside were gone. There are no detailed fossil records from this period. The environments that had produced the Hell Creek Formation no longer existed in the same form. The lowland floodplains were changed. The rivers ran differently. The food web that had structured every interaction for millions of years had been dismantled from the bottom up. What the record shows, resuming after a gap that the paleontological resolution is too coarse to fill, is that the survivors expanded. The first mammal of substantial body size appears in the fossil record a few million years above the boundary. The first hoofed mammal appears shortly after. The first primate, tentatively identified from fragmentary teeth, appears in the earliest Paleocene. These are not the children of a world that was cautiously recovering. They are the children of a world that was, in ecological terms, rebuilding itself from almost nothing, as fast as natural selection could manage. TANIS shows the first 13 minutes of that process. It is the only place in the world where the first 13 minutes can be seen. The recovery the 66 million years that followed is documented, in varying degrees of completeness, in sediment layers on every continent. What connects the first 13 minutes to the present moment is a record that is, in most of its extent, incomplete. The record always is. The record only ever is. This is not a limitation of the science. It is the nature of what the past is, something that occurred once, left partial traces, and can only be partially recovered. The TANIS site is exceptional, not because it is complete, but because it is less incomplete than almost anywhere else. The morning of 66 million years ago is still being recovered there. It will be for years. There is a question that the literature returns to, and that the literature cannot answer. The question is whether the world we inhabit is the world that was supposed to exist, or, to set aside the word supposed, whether the world we inhabit is the most probable outcome of what came before it, or one of many possible outcomes, or an unusually unlikely one. The records as currently understood suggest the third. The chain of conditions required to produce our particular biosphere, the impactor's origin, its composition, its trajectory, its angle, its arrival time within the year, its target rock, the prior weakening of the biosphere by volcanism, the seasonal state of the surviving lineages is, when examined in combination, improbable. How improbable is not a question the current literature has fully answered, partly because the necessary probability calculations require assumptions about baseline rates that are themselves uncertain. What is clear is that each factor, taken individually, was in a range that applied to a minority of possible cases, and that the factors were, as far as can be determined, statistically independent of each other. The question has a name in philosophy, though it is rarely applied to this specific case. The anthropic principle, in its various forms, addresses the observation that the conditions we find ourselves observing are, by definition, compatible with our existence because, if they were not, we would not be here to observe them. In this sense, there is no mystery. Of course, we find ourselves in a world where the asteroid struck the right rock at the right angle in the right season, because in the worlds where it did not, there is no we to ask the question. The question selects for its own answer. This is true. It is also, in some ways, less satisfying as a resolution than it might appear. It tells us that our existence was possible. It does not tell us how probable it was. It does not tell us whether the path that led here was one of many equally probable paths, or one of very few. Any specific outcome, viewed from after the fact, was unlikely at the time it occurred. The precise configuration of every atom in your body, at this exact moment, was at any prior point in the history of the universe astronomically unlikely. This is not a meaningful observation about your particular existence. Every outcome is, in retrospect, improbable. The probability of something happening cannot be inferred from the fact that it happened. But there is a distinction, perhaps, between outcomes that are improbable in the way that any specific outcome is improbable and outcomes that depended on a margin as narrow as 13 minutes in a 24-hour day. Most major evolutionary transitions in the fossil record do not appear to have turned on intervals of this brevity. The Cambrian explosion unfolded over tens of millions of years. The evolution of the vertebrate eye took millions of years. The emergence of flowering plants took millions of years. These were long, gradual processes with wide margins of time and many contributing factors. The KPG boundary was different. It was not a gradual transition. It was a threshold event, a moment in which conditions on one side were one thing and conditions on the other side were another. And the transition between them occurred faster than any geological process previously known to have caused a mass extinction. The margin was 13 minutes. The consequences were the biosphere we now inhabit. The records will continue to accumulate. New fossil sites will be found. New analytical methods will be applied to existing specimens. The 13-minute figure will be refined. The probability calculations that Kaiho and Oshima began will be extended. The story of what happened on the spring morning 66 million years ago will become, in its details, clearer than it currently is. Whether it will become more comfortable, whether it will produce a narrative in which the emergence of our particular biosphere and our particular intelligence begins to look less improbable, is not something the records can currently predict. What can be said is that we exist within a record that almost did not exist. The biosphere we belong to formed in the gap left by a different biosphere that almost continued. The intelligence we possess emerged in space that was almost still occupied. The questions we are now asking about the asteroid, about the 13 minutes, about the Dinosauroid in storage in Ottawa, could only be asked because of how the asteroid arrived, in what season, at what angle, in what minute of what day. The records do not resolve this, they only continue. New fossils are recovered every year. The picture sharpens, slowly. The 13-minute window becomes more certain. The Dinosauroid remains in storage. The boundary layer, 3 millimeters thick, remains in the rock, below the present and above the past, separating two worlds on the same planet. Somewhere in the world tonight, someone is standing over a rock layer just like it. Somewhere, a drill core is being extracted from a KPG boundary site, and the iridium layer is being identified under a microscope, and the records of a spring morning 66 million years ago are being read again. The record does not say where. It does not say by whom. It only says that the question is still open and that the question is still being asked. The record has not yet decided what to make of this. Perhaps it never will. What remains, in the absence of a conclusion, is the record itself. The Tanis site, the iridium layer, the troodontid brain case, the Dinosauroid in storage, the 1982 paper that asked an unanswerable question and refused to take the silence for an answer, the 2017 paper that calculated the 13%, the 2022 paper that read the season from the chemistry of bones. These are not stories. They are recovered fragments. They accumulate without resolving. This is, in the end, what the record does. It accumulates. Each generation of researchers adds to it, refines it, extends it backward and sideways into regions that earlier generations could not access. The picture becomes more detailed without becoming more complete. The 13-minute window was not known to be the 13-minute window until 2017. The season was not confirmed until 2021 and 2022. The angle was not calculated until 2020. The details that make this story what it is that allow the coincidence to be appreciated in its full specificity are recent recoveries, some of them made in the last few years. There are details still unrecovered. There will be for as long as the discipline continues. The question that cannot be answered, the question of what would have happened in the alternate timeline, of what the Troodontids would have become, of whether the biosphere we inhabit is improbable or inevitable, does not need an answer to be worth asking. The asking of it is itself a form of data. It indicates what we have become, 66 million years after the spring morning that made us possible. It indicates what kind of beings we are, the kind that find themselves in possession of intelligence and use that intelligence to reconstruct the circumstances of their own origin and stand at the edge of what the record shows and look into the silence and ask what is there. The silence does not answer. It has not answered. The records continue. The land in North Dakota is quiet now. The Tanis site is closed to the public. The leg of the Thescelosaurus has been removed for study, cataloged, measured, photographed from every angle, and placed in storage alongside the paddlefish and the sturgeon and the fragments of pterosaur membrane and the ammonite shells from a sea that no longer exists. The riverbed that briefly held an impossible record has been excavated, in some sections, down to the iridium layer itself. In other sections, it remains undisturbed, as it has remained for 66 million years. There are still fossils there that have not been recovered. There will be, perhaps, for as long as the site endures. In Mexico, the Chicxulub crater is buried beneath a kilometer of younger rock, offshore from the northern Yucatan Peninsula. There is a small town near its center that gives the crater its name, Chicxulub Puerto, a fishing village on the Gulf Coast. Most residents of the surrounding region are not aware that they live on top of the largest, confirmed impact structure of the past 100 million years. The crater is invisible from the surface. Its existence is known only through survey reports, academic papers, and the rock cores of drilling expeditions. It is documented in detail in archives that most people will never access. It is one of the most consequential geological features on the surface of this planet, and it is invisible. In Ottawa, the dinosauroid model remains in storage at the Canadian Museum of Nature. It is not on display. It has not been widely exhibited for many years. It is an object that occupies a space in the record that the record itself is uncertain about, neither proven nor disproven, neither a prediction that can be tested nor a speculation that can be dismissed. It exists at the boundary between what the fossil record shows and what it implies. It is approximately the height of an adult human. The biosphere it depicts did not occur. The biosphere that did occur is the one in which this record is being read somewhere, at this hour, in a city or a quiet room, or a place far from both. The local time is whatever it is. The listener is one of the descendants of the small nocturnal mammals that survived the spring of 66 million years ago, in the southern hemisphere autumn, in the burrows in the dark. The 13 minutes did not give us this world. The 13 minutes only made it possible. What followed was 166 million years longer than all of recorded history. What followed was the slow expansion of small animals into vacated space, the quiet, unhurried work of evolution filling an emptied world. What followed was the emergence of one particular order of mammals, and then one particular family within that order, and then one particular species, unremarkable in body size, unremarkable in physical capability, distinguished only by the particular complexity of its neural tissue, and then language, and then writing, and then records the accumulated attempt to preserve what happened, to hold it against forgetting, to keep the morning of 66 million years ago available to any mind that wanted to examine it. The records show that the examination is ongoing. The papers are still being published. The rock cores are still being extracted from the seafloor near the Yucatan. The Tanis site is still being excavated, carefully, with the knowledge that what lies beneath the next centimeter of sediment may change the story. Every year, the picture becomes slightly more detailed. Every year, the 13 minutes becomes slightly more confirmed. The Hell Creek Formation, the river valley where all of this was buried, continues to erode. The Badlands expose new material with each season of rain and frost. Somewhere in the formation, there are fossils that have not yet reached the surface. Some of them will. Some will be found. Some will add to the record. The records do not say where the next 13 minutes will fall. They never have. A note before the record continues. This channel exists because of the people who return to it. If you find that the quiet examination of things long forgotten is something you value, the slow reconstruction of what was, the careful accounting of what might have been, the like and subscribe buttons, or how that interest is recorded. And in the comments, if you would, the location and the local time. The archive keeps its own log of where these files are read and when. That log in practice has proven to be something more than a count. It is a quiet record of its own of people, in hundreds of cities and dozens of countries, sitting with the same questions at the same hour. It has been a quieter comfort than expected. The record continues.